Good morning. Um, this is the topic on cuts and matrices, and I'll be taking this topic. So, what is a cut set? So, cut set is defined as a set of edges upon whose removal from a connected graph G, the graph becomes disconnected. We've learned this in module 4, and it also partitions the vertices of a graph into two disjoint sets. So, what we'll be looking into, like in this slideshow, would be the cut set matrix. So the cut set matrix is defined as C is equal to C of ij, and the rows in the cut set matrix correspond to the cut sets and the columns correspond to the edges of the graph. So how you do this is, let's look at an example. So this is a graph. These are the cut sets that are marked over here in dotted lines. This is the cut set matrix. So let's look at the first cut set. The first cut set is, it cuts the edge H, and you can see there's a 1 over here and zeros for every other edge. And the next one is AB. So A and B's have 1s and the rest all have zeros. The third cut set has EC, and like as you can see, E and C are notated as 1 over here, the rest are 0, and so on and so forth. So you can look through this and you can see that the edges that are cut by the cut set are marked as 1, and the ones that are not cut by the cut set is marked as 0. So there are some observations that we can get from the cut set matrix that we just saw right now. Like I said, the rows and columns correspond to cut sets and edges, and each row in a cut set matrix is a cut set vector. That is, each row is called a cut set vector, and you can see that all a column with all zeros corresponds to an edge forming a self loop. But here you can see there are no columns with zeros, complete zeros, which means that there are no self loops. Like you can see in the previous slide, you can't really see any zeros in the columns because it is not uh, there are no self loops in the graph. So the next one is, parallel edges produce identical columns in the cut set matrix, and columns A and B in the cut set that we just saw right now, the example that we saw, are parallel edges, so they have identical columns. And so right now let's look at the next property. In a non-separable graph, every set of edges incident on a vertex is a cut set. Therefore, every row of an incidence matrix AG is included as a row in the cut set matrix. Right here you can see a very simple connected graph, which is a rectangle, and you can see that this is the incident matrix, like we have learned previously to draw the incident matrix. These are the incident matrices with the vertices and the edges, and this is the cut set matrix. You can see that they're identical because this is the property that gives us the fact that they'll be identical. As you can see, this will be required from the next point, that the rank of the cut set matrix and the incident matrix are equal, which is our next point. So the rank of the cut set matrix and the incident matrix will be equal, or the rank of the cut set matrix will be greater than the rank of the incident matrix. So we hereby reach a property in which we can say that the rank of the cut set matrix will be greater than or equal to n minus 1. Here n is 4, so n minus 1 will be 3, and we have our rank of the cut set matrix as equal to 3. And the next property is that the number of edges common to a cut set and a circuit is always even. We learned this as a theorem, and therefore every row in C is orthogonal to every other row in the cut set matrix, circuit matrix, of graph H, provided the edges in both B and C are arranged in the same order. So basically the dot product of the matrix and the transpose of the other matrix will give you 0. And we have seen the previous equation where we can say that the rank of C is greater than or equal to n minus 1. And over here we have the Sylvester's theorem, which we have learned before. Sylvester's theorem just briefly gives us this relation, that the rank of the circuit matrix, and the rank of the cut-set matrix will be less than or equal to the edges. And we know for a connected graph, the rank is n minus 1. And applying this over here, we get the rank of B as E minus n plus 1. And we have the rank of C from this equation as less than or equal to n minus 1. When we combine this equation and the previous equation number 1, we get that the rank of C is equal to n minus 1. So we come to the theorem. The theorem says that the rank of the cut-set matrix is equal to the rank of the incident matrix, which we've already seen, which equals to the rank of the graph G. So the cut-set matrix will have redundant or linearly dependent rows. So we usually find the fundamental cut-set matrix. So the fundamental cut-set matrix will be n minus 1 by E order, and it's basically a matrix that corresponds to such that each row corresponds to the set of fundamental cut sets of some spanning tree. And this is the relation that we'll get, where I is the incidence matrix of order n minus 1, and this is the cut set. So you can see over here, this is the graph that we've seen before, and yes, these are the branches in this. This is a spanning tree of the previous graph. So the branches over here are 1, 3, and 2. Sorry, 4, E4, E3, and E2, and this is the chord that is not included in the spanning tree. And for a fundamental cut-set matrix, there are two requirements. It has to make the graph disjoint. That is, if we remove this on this edge and this edge, this graph, this vertex becomes isolated. So this becomes a disjoint graph. It makes it into two disjoint graphs. Similarly, the same case over here. And that is the first requirement. The second requirement is that the cut set should only contain one chord and one branch, and the rest are chords. And over here you can see that C1 has one chord and one branch, and one chord and one branch. It can contain as many chords as it wants, but it can only contain one branch, fundamental cut sets. So over here we only have two fundamental cut sets, and when we draw the fundamental cut set matrix, it looks like this.
Here we will see the relations between reduced incidence matrix AF, fundamental circuit matrix BF, and fundamental cut-set matrix CF. Consider this as a spanning tree with the edges B, C, D are the chords of the spanning tree, and A, E, G, H, and F are the branches of the spanning tree. Here, AF represent the reduced incidence matrix having two submatrices AC and AT. AC is the submatrix of chord, and AT is the submatrix of a branch, and BF, which is the fundamental circuit matrix having two submatrices I3 and BT. I3 is the identity matrix of order 3, and BT is the submatrix of branches. And at last, CF, which is the fundamental cut set matrix having two submatrices CC and I5. CC is the submatrix of chord, and I5 is the identity matrix of order 5. I am not going in detail with this because you have already learned how to construct these matrices. These are the equations that we already learned. Here, I mu and in minus 1 indicates the identity matrix of order mu and n minus 1 respectively. Since the columns in AF and BF are arranged in same order, that we already seen in the last slide, that AF, BF and CF have the same order. And here we can apply the property mode to arithmetic. The property is that A dot B transpose equal to B dot A transpose equal to 0. If we apply here, we get AF dot BF transpose equal to 0. And we substitute the values of AF and BF, we get AC AT dot I mu BT transpose equal to 0. And if we take the transpose inside, then we get AC AT dot I mu divided by BT transpose equal to 0. And we take the dot product, we get AC plus AT dot BT transpose equal to 0. Since AT is non-singular, there will be existing AT inverse. So we need to multiply AT inverse on the both side of this equation. By multiplying with AT inverse, we get AT inverse dot AC equal to minus BT transpose. Since in mode 2 arithmetic, minus 1 equal to 1, so we can write the equation as BT transpose equal to AT inverse dot AC, which is considered as equation number 4. Then similarly, since the columns in BF and CF are arranged in the same order that we already seen before, we can apply these steps over here and see thereby CF dot BF transpose equal to 0 by applying the property of mode 2 arithmetic, that is AB transpose equal to BA transpose equal to 0. And then we get, by substituting the values of CF and BF, we get CZ IN minus 1 dot I mu by BT transpose by taking the transpose inside equal to 0, and then CC equal to minus BT transpose, and by taking the mode 2 arithmetic property of minus 1 equal to 1, we get CC equal to BT transpose. And we already seen that in the equation number 4, BT transpose equal to AT inverse dot AC. So we substitute the value here. So we get AT inverse dot AC. Then that is equation number 5. From equation number 4 and 5, we get that BT transpose equal to CC equal to AT inverse dot AC. By this, it leads to certain conclusions that given A or AF, we can readily construct BF and CF starting from an arbitrary spanning tree and its subgraph AT in AF. If we check the equation here, we can see that BT transpose equal to CC equal to AT inverse dot AC. If we have AF means we know the values of AT inverse dot AC. And if we substitute the values over here, we get the corresponding values of CC as well as BT transpose, and thereby we can construct BF and CF. And the second conclusion is that given either BF or CF, we can construct the other. Since BF determines a graph within two isomorphism, so does CF. Here also, if we know BF means we also know the values of BT transpose, and thereby we get the values of CC and AT inverse dot AC. Then by knowing the value of CC, we can construct the CF. As we all know, the equation for CF is CC dot IN minus 1. So it is easy to construct CF. And also in the same way, if we know the value of CF means if we have CF means we know the value of CC, and substituting over here we get the value of BT transpose, and thereby we can find out BF. And the equation for BF is that BT dot I mu. And the third conclusion is that given either BF or CF, AF in general cannot be determined completely. As we know that the equation for AF is AT dot AC. So over here, BT transpose equal to CC equal to AT inverse dot AC. If we know BF or CF means we only know the value of BT transpose or CC. And here we need the dot product of AT inverse dot AC. So it is not possible to determine completely the value of AF. And that's it. Thank you.